Good day, learners. Welcome to our physical sciences lesson. My name is Amenim Kize. This lesson is brought to you by Sci-Bono Discovery Center in collaboration with Gauteng Department of Education. Right, grade 11s, our focus today is still on mechanics. Even last week we were focusing on mechanics. So this week we're also going to focus on mechanics, but the subtopic under mechanics will be different kinds of forces, free body diagrams and force diagrams, right? So this is our exam guide, or this is what we need to cover under different kinds of forces, also under free body diagrams and force diagrams, right? Then it should be different kinds of forces, which is weight, normal force, frictional force, applied force, right? And also what? Tension, okay? Then defining normal force, define the frictional force, and then we have two types of frictional forces, which is your static frictional force and your kinetic frictional force. So we have to define that and do some calculations around that. And then also talking about what the relationship between the normal force and the frictional force, okay? Then when it comes to free body diagrams and force diagrams, it will be, drawing force diagrams and free body diagrams, for all the scenarios. So we'll address the scenarios as we move on, okay? Right. Then when it comes to forces, learners, because our our subtopic today is different kinds of forces. Remember, when it comes to a force, you did forces in grade 9, grade 10 also. You did forces. Even this year, you've been dealing with forces. But what we know is that a force is a vector, right? So it has both magnitude and a direction, okay? So force is a vector. It has both magnitude and direction. But in simple ways, right, what is a force? A force is just pull or push. All right, I think you are aware of that. It's what you did in grade 9. Okay, then we have two types of forces. We have non-contact forces, okay, and also the contact forces. Then when we talk of non-contact, right? So non-contact forces, those are forces that act over a distance, okay. Then when it comes to contact forces, those are forces exerted by objects that are in contact with each other. All right. So we have contact and non-contact forces. So forces that are divided into two categories. We have non-contact and contact forces. All right. So non-contact, they act over a distance, and then the contact forces, those are the forces exerted by objects that are in contact, okay? Right, then the examples here, we are given the examples of non-contact forces. Then under non-contact forces, we have magnetic forces, right? So that is one of the examples of a non-contact force. So magnets, they exert forces on each other without physically touching each other, all right? So that is why we are saying a magnetic force, it's a non-contact force. So right, then electrostatic force, charges, right, they exert forces on each other without physically touching each other, right? So then the force that charges exerts on each other is called the electrostatic force. Then the gravitational force, right? So the gravitational force, which is weight, right? So it's also a non-contact force. So these are examples of non-contact forces. But when you talk of a non-contact force, those forces, they act over a distance. So there's no physical contact, okay? There's no physical contact when it comes to objects. All right. Then when it comes to contact, there's physical contact, right? So those are the forces exerted by objects that are in contact, okay? For example, the applied force, the frictional force, the normal force, the tension, air friction, and compression, right? So forces are divided into two categories, right? We have non-contact and contact forces, all right? Then let's start with a normal force. By now we already know that a normal force is a contact force. So there must be contact between two objects for us to have a normal force. All right, it is a a contact force. Okay, that is a normal force, right? So when we talk of a normal force, learners, right, very very important, right? We already know the symbol for force, right? The symbol for force, it's F, ne? I hope you are aware. And then the SI unit is what? Is Newton. So this is the SI watt unit. So the symbol for force is capital letter F, and then force is measured in what? In newtons. So there are two categories, all right? We have contact and non-contact. So we've given examples. By now, I believe you understand when we talk of a contact force, what do we talk about? When we talk of a non-contact force, what do we talk about? Very, very important. It's very, very important to understand that, learners. Right now, going straight to those different kinds of forces, let's start with the normal force. So the normal force, the SI unit for, so not the SI unit, but the symbol for normal force is capital letter N, right? That is the accepted what symbol for what? For the normal force. But sometimes you can also use what Fn. But actually, according to our exam guide, right, or according to our CAPS document, right, so the symbol for normal force is capital letter N. Okay, so capital letter N is the symbol for normal force. And what is normal force, right? Is the force or the component of a force which a surface exerts on object, exerts on an object with which it is in contact and which is perpendicular to the surface. All right, so that is the normal force. The normal force, the symbol is capital letter N, or we can also use Fn. Is the force exerted by what? By the surface on an object that is in contact with, and this force always acts perpendicular to what? To the surface. All right, so here we can even give examples. Look at this, right? There are books right on top of what? Of the table. So here we are having the table, and then these are the books, right? So when we talk of the normal force, right? Normal force, that is the force exerted by the surface on an object that is in contact with, ne? And then this force always acts perpendicular to what? To the surface. So here, the surface here is the table, all right? So when we talk of the normal force in this case, actually it is the force exerted by the table on what? On the book, all right? Because we are saying it's a force that exerted by the surface on what? On an object which is in contact with, right? So the book and the surface of the table, or the table, right, is they're in contact. Okay, so if they're in contact, we can talk about what they're the contact forces. And one of the contact forces that we are looking at right now is the normal force, right? And we are saying is the normal force is the force exerted by the surface, which is the table, on what? On the book. Okay, so by the surface on what? On what? On the book, or the table on what? On the book. Okay, and then this force always acts perpendicular, so we must always draw it perpendicular to what? To the surface. Very, very important. So this is what? The normal force, which is the force in this case, the force exerted by the table on what? On the book, right? So the book on top of the table. What is the surface there? Is the table. Then when we talk of the normal force, is the force exerted by the surface, which is the table in this case, on what? On an object, which is the book, or the books in this case, right? So that is going to be what? The normal force. So this is how we have to represent normal force in this situation. All right, then whether, very, very important, right? So whether the object is on the horizontal surface, for example in this case, right, the book is on the horizontal what? Surface, right? Or whether the object is on the inclined plane. You can see this block is on an inclined plane, right? Normal force is always acting perpendicular to what? To the surface. Remember, it is the force exerted by what? By the surface on what? On an object, right? And it always acts perpendicular to what? To the surface. So here we're expecting 90. Even here we're expecting what? 9. So that is going to be what? The normal force. So it's a force that is always acting perpendicular to what? to the surface. So if the surface is a horizontal surface, it still acts perpendicular to the surface. If the surface is an incline, then it will also still act perpendicular to what? To that inclined surface. Very, very important. That is the normal force. Normal force is one of the forces that we are going to look at, or that we are looking at under different kinds of of forces. The symbol is N. The SI unit, remember, it's a force. So the SI unit is what? It's newtons, right? And what is normal force? Is the force exerted by the surface on an object that is in contact with, and it always acts perpendicular to what? To the surface. So we will talk about the normal force, right? If there's what there's about a contact, right, between two objects, okay? If there's contact between there's contact between two objects, and also the surface, either it is a horizontal or inclined plane. All right, so it's what we are going to focus, right? So I think we are fine with the normal force. It always acts perpendicular to the surface, whether the surface is an incline or the horizontal surface. All right, then your normal force will always act perpendicular to to the surface. When it comes to vertical plane, we can't talk about we can't talk about the normal force because there's no surface there, right? For example, an object thrown vertically upwards in the air, right? So we cannot talk about what the normal force there. Why? What is normal force? Is the force exerted by the surface. So when an object moves vertically upwards, do we have the surface? No, right? So the object actually must be in contact with the surface for us to talk about the normal force. Very, very important. It's a force exerted by the surface on an object, and it acts perpendicular to to the surface, right? Then now let's move to frictional force. So it's another kind of a force. And then frictional force, different from the normal force. Normal force, N, that is the symbol, and it always acts perpendicular to the surface. It's the force exerted by the surface on on an object. For example, if you talk of the normal force, a person standing on the floor, right? So the person standing on the floor, obviously the person, right, it's in contact with with the floor. All right, so there will be a force exerted by the floor on the person. So that force exerted by the surface on an object, floor on the person, it's going to be the normal force. So I think we are fine with the normal force. It's a force exerted by the surface on an object which is in contact with, and it always acts perpendicular to the surface, right? Now let's move to frictional force, right? The definition of frictional force. So frictional force, the symbol is small letter F. Symbol is small letter F. Capital letter F, we use it for force, right? So, or applied force, okay? But when it comes to frictional force, we use small letter F. I hope we are fine with that. This is from the exam guide or from the CAPS document, right? So these are accepted to labels, right? So frictional force is the force that opposes the motion of an object, and it always acts parallel to the surface. It's simple, it's straightforward, this one. This force always opposes the motion of an object, right? So if you have an object on the horizontal plane, right, for example, and then this object is moving maybe to the right, that is the direction of motion. Your frictional force will act in the opposite direction, which is to the left. Even when it comes to an inclined plane, if an object is moving up the slope, right, your frictional force will act in which direction? Down the slope. So it's a force that opposes the motion of an object. If an object is moving vertically upwards, right, in the air, we can talk about air friction there. So the air friction will act in the opposite direction. Air friction will act in the opposite direction. So what is frictional force? It's the force that opposes the motion of an object, and it acts parallel to the surface. So it's always parallel to the surface. You can see here, my frictional force is parallel to the horizontal surface, right? My F there, which is my frictional force, is parallel to an inclined plane. So it's always it acts parallel to the surface. Very, very important. So what is frictional force? It's a force that opposes the motion of an object, and it acts parallel to what? To the surface. So if an object is moving to the left, then the frictional force will act to the right. If an object is moving vertically downwards, the frictional force opposes the motion of that object, so it will act vertically what? Upwards. If an object is moving down the slope or down the incline, right, your frictional force will act in the opposite what? Direction. So please, grade 11s, name, frictional force is not the force that opposes force applied, right? Frictional force is not the force that opposes force what? Applied, but it is the force that opposes the motion of what? Of an object, and it acts parallel to what? To the surface. Then another thing that we need to know that frictional force is proportional to the normal force. So we'll talk more about that moving forward. So frictional, there's a relationship now between what? Frictional force and what? And normal force. So based on this, they're saying frictional force and normal force, they are proportional to each other. So which means that actually frictional force depends on the normal force, and when you increase the normal force, right, what happens to the frictional force? Frictional force also what? Also increases. Then the frictional force is independent of area of contact, also independent of the velocity of what? Of motion. Whether the velocity is increasing or decreasing, you know, the frictional force does not depend on that, but it depends on what? On the normal force. So if the normal force increases, even the frictional force will what? Will increase, for example. All right. So here we are talking about the frictional force, which is the force that opposes the motion of an object, and it acts parallel to what? To the surface. Okay. Then the symbol is small letter F, and then the SI unit is what? Is newtons. Remember, it's a force. All right. And another thing which is important about this slide is that frictional force depends on normal force, so they are proportional, right? So if you increase the normal force, even the frictional force that acts on an object is going to do what? To increase, right? Then frictional forces, okay, we are saying it's a force that opposes the motion of an object. So if this is the motion of what? Of an object is to the right, then your frictional force will act in which direction? To the left. So it's a force that opposes the motion of what? Of an object. If an object is moving towards the right, for example, your frictional force will act in the opposite what? Direction. So another thing which is very, very important, né? So there are certain weights that they can that they can use to show that there's friction in that surface. Okay, so sometimes they can use weight rough. In most cases, they use weight rough. This is a rough surface. This is a rough horizontal surface. This is what? A rough inclined plane. You understand that? Okay. So if the plane or either horizontal inclined, right, they are rough, it means that there's frictional force there, like it or not. But if they're going to say this is a smooth surface or this is a frictionless surface, so obvious there's no friction, right? But if immediately when they say the surface is rough, it means that there's frictional force. There's a force that opposes the motion of what? Of an object, and that force acts parallel to what? To the surface. And that force depends on what? On the normal force. Very, very important. Ne? So when we talk of frictional force, it's a force that opposes what? The motion. This is the motion of that object. All right. It's a rough surface which shows that there's frictional force. Then your frictional force will act in the opposite what? Direction. That is frictional force. Okay. The symbol is small letter F. And then the SI unit is what? Is newtons. All right. It's a force that opposes what? The motion of an object, and it always acts parallel to what? To the surface. Okay. Then there are two types of frictional forces. It's the static frictional force, and then the symbol for it is Fs, and then the kinetic frictional force, and the symbol for that is what? It's Fk. All right. So let's start with the static frictional force. Static frictional force. So static frictional force is still frictional force. I hope you understand that. It's a force that opposes what? The motion of an object. That is your frictional force. And it acts parallel to what? To the surface. Right. So your static frictional force, Fs, that is the symbol, is the force that opposes the tendency of motion of a stationary object relative to what? To the surface. So static means stationary. All right. So if you have an object on a rough horizontal surface, okay, you have an object on what? The rough horizontal what? Surface. Okay? So if you have an object, for example, you have an object of M, and then this is the rough horizontal what? Surface. So then let's say you apply a force, maybe of 50 watt newtons, right? Then if you apply a force of 50 newtons and the object does not move, remember it was going to move if the surface was frictionless. So but the surface here is what has what? It's rough, or it has what? It has friction, right? So if it happens that you apply a force of 50 newtons to this object, but the object still does not move, the reason why it does not move is because of the static what? Frictional force. All right. So what is important here, you should know that when you apply a force, right, and the object does not move, right? When you apply a force and the object does not move, it means that the force that you are applying, force applied, right, will be equal to what? Frictional force, but acting in opposite what? Direction. So if you are applying 50 newtons, right, even this one would be what? 50 watt newtons, because the object is not moving. So the reason why is it not moving is because of the static frictional what? Frictional force. So if you apply a force of 50 newtons and the object does not move on a rough what? Surface, you should know that the force that is being applied there is equals to what? The static what? Frictional force. Very, very important. So you can increase this to 60 if again the object does not move, right? Then it means that your F or the frictional force is what? It's also what? 60 newtons. Okay? So you have a static frictional force if an object is at rest on a rough surface. You have a static frictional force if an object is at rest on a rough what? Surface. I hope it's making sense. You have a static frictional force. The word static comes from the word stationary. All right. So you'll have a static frictional force, right? If an object it does not move on what? On that rough horizontal surface or inclined what? Surface. Very, very important. That will be a static frictional force. Static means stationary. So you'll only observe static frictional force if an object is at rest or is stationary on a rough horizontal what? Surface. Is stationary or on a rough horizontal what? Surface, right? Then that is the static frictional force, which is the force that opposes the tendency of motion of a stationary object relative to what? To the surface, right? So this is what I was talking about, learners. If a force F is applied to a body parallel to the surface, does not cause the object to move, right? F is equal in magnitude to the static frictional what? Force. So it's what I was trying to explain here. So you have an object on a rough horizontal surface, is stationary, right? Then you apply a force of 50 newtons, but the object still does not move, right? If it does not move, right, the type of friction that we are still talking about there in that moment is the static frictional force, right? And the magnitude of the force that you have applied, since the object does not move, will be equals to the magnitude of what? Of the static frictional force. I hope it's making sense, learners. Okay, right. Then now let's move again. We are still on static frictional force. Then for me to explain this bullet, all right, I'm having an object again on a rough horizontal surface. Initially, let's say I'm applying a force of 10 newtons. The object does not move. Okay, what does that mean? It means that the static frictional force is still what? 10. I increase the force applied on this object to what? Maybe to 30. Let's say still the object does not move. Okay, so if an object does not move, it means that even the static frictional force is going to be what? 30 newtons, right? Then in a case where now when I apply a force, right, and that force overcome the frictional force, right? Remember what is going to happen. The object will start to move, right? Let's say you apply a force of 50 newtons, and then the object starts to do what now? To move. Okay, so when an object obviously is in motion, then we'll talk about the different type of frictional force. Okay, then I want to explain the issue of what now? Maximum static friction. I've explained the static friction, right? The definition of static friction, right? You apply a force, for example, and then the object does not move, right? So the reason why it does not move is because the force that you are applying, right, is equals to the magnitude of the force of static friction. Okay, then if you keep on increasing the force that we are applying, right, and still the object does not move, here we have increased it to what? To 30, but still the object does not move. It means that your Fs is still what? 30 newtons. But there will be a point when we keep on applying a force, there will be a point where the force now that we are applying overcome what? The static what? Friction. Okay, then at that point we have what we'll call so let's say this is F3, then we apply a force of 50 newtons. At that point we have what we call maximum static what? Friction. Okay, we have maximum static what? Friction. So the maximum static friction, obvious, it should be greater than what? The force that is being what? Applied, which is maybe, let's say here it's what? Maybe 70 newtons. Okay, then learners, what is maximum static friction? Is the force that opposes the motion of an object just before the object starts to move across what? The surface. Okay, maximum static frictional force is the force that opposes the motion of an object just before actually it should be what? A force that opposes let me put it nicely here, because our static frictional force is the force that opposes the tendency of motion of a stationary object relative to the surface, right? So this one is just before the object starts to do what? To move. So that is the force that opposes the motion of what? Of an object just before the object starts to do what? To move across what? Across the surface. So that is the maximum what? Static friction. Okay, that will be the maximum static what? Friction. Okay, so yeah, so what is important here is that when you apply a force on an object and an object does not move, the force that you are applying, or the magnitude of the force that you are applying, will be equal to the static frictional force, or the magnitude of the static frictional force. So when you keep on increasing that force, right, and still the object does not move, if you have increased it maybe by 5, we are moving from 10 to 15, but the object still does not move, what will be your static frictional force? Is still what? Is still 15 newtons. Okay, then obviously the object will remain what? Stationary. This thing actually takes us back to forces at equilibrium, right? We did forces at equilibrium, right? So if I'm having a force of 10 newtons, but the object does not move, it means that the forces are at equilibrium. It means that the frictional force is also what? 10 newtons. Because if you have 10 newtons and 10 newtons but acting in opposite directions, what will be the net? The net there will be what? Will be 0 newtons. So if the net is going to be 0 there, it means that that object will remain at what? At rest. Okay, then you increase the force to what? To 20, but still the object does not move. It means that the forces are still at what? At equilibrium. Your force applied is 20, even the frictional force is what? Is 20, right? Then if you apply a force and now the object starts to move, right? So it means that the force that you're applying there overcome what now? Overcome friction, okay? Then just before an object will start to move, we have what we call the maximum static what? Friction, which is the force that opposes the tendency of motion of a stationary object, right? Just before an object will start to do what? To move, right? So that is the maximum what? Static what? Friction. And we can calculate this maximum static friction. How do we calculate the maximum static friction? It's Fs max equals to mu Sn, all right? Where Fx max is the maximum static frictional force in what? In newtons. Mu s is the coefficient of static what? Friction. Obvious n there will be what? The normal force. You can see that frictional force and normal force, they are proportional to what? To each other. So if you increase the magnitude of the normal force, we are expecting the magnitude of the frictional force also to increase at constant what? Coefficient of friction. Okay. So I've talked about the static frictional force, all right? I've talked about the maximum static frictional force. Now let's move to kinetic frictional force. So these are the two types of frictional forces, right? So frictional force, that is the force that opposes the motion of an object, or the motion of what? Of a moving object relative to what? To the surface. Okay, that is the kinetic frictional force. That is the force that opposes the motion of a moving object relative to what? To the surface. So I've talked about the static friction, which is the force that opposes the tendency of motion of a stationary object relative to what? To the surface. Then maximum static friction, that is the frictional force just before an object will start to do what? To move, or the force that opposes the tendency of motion of a stationary object just before an object will start to move relative to what? To the surface. Right, then now we are talking about the kinetic frictional force, which is the force that opposes the motion of a moving object relative to what? To the surface. So note this: if the applied force exceeds Fs max, right? So if the applied force exceeds what? Fs max, a resultant net force accelerates what? The object. The object is in motion now, and then it will experience what? The kinetic what? Frictional force. What are they trying to say here, right? You have your what? Your let's say you apply a force of what? So here it should be 50-50, ne? Okay, maybe 50-45. Okay. Right. So what are they saying here? If the applied force exceeds Fs max, resultant net force accelerates the object is in motion, and then now it experiences what? Kinetic frictional what? Frictional force, right? So here what is happening? We are applying a force of 10 newtons. The object still does not move. Then it means that the frictional force acts in the opposite direction with the same magnitude, okay? You apply a force of 30, the object still does not what? Does not move. Then you apply a force of what? Of 50, and then the object suddenly moves. Okay? Right? So if the object suddenly moves, or the object now is in motion, we no longer talk of what? Of static frictional force or maximum static frictional force, but we talk of what? Of kinetic what? Frictional force. That is very, very important. Ne? So I'm applying a force of 50 newtons, and then the object starts to do what? To move. But there is that frictional force just before an object will start to do what? To move. Okay? So if you apply a force, right, that will be greater than the static frictional force, the object will start to do what? To move. Okay? So, and then just before an object will start to move, we talk about what? The maximum static what? Friction. Okay? Then how do we calculate the kinetic frictional force? We use Fk mu Kn, where Fk is the kinetic frictional force, all right? And then the mu K it's the coefficient of kinetic friction, and then N is what is the normal force. Okay, so I've talked about two types of frictional forces, right, which is your static frictional force. Static means stationary, right? Kinetic means dynamic motion. All right, so your static frictional force, that is the force that opposes the motion of an object. It's the force that opposes the tendency of motion of a stationary object relative to the surface, right? Then we have what we call the maximum static friction, which is the force opposes the tendency of motion of a stationary object just before an object will start to move relative to the surface. Okay, then that is the maximum static frictional force. Then the kinetic frictional force, that is the force that opposes the motion of a moving object relative to the surface. Then now note the relationship, right? So let's look at this graph. Okay, you are applying a force here, right? You are applying what? A force. A force of 0 newtons. Even the frictional force, it's going to be what? 0 there. You apply a force of 10 newtons, right? Can you see that this is force applied? Okay, so what is your dependent variable here? Is frictional force. Your independent variable is what? So this is dependent, and then this is going to be what? Independent. All right, so you are applying a force here, right? So it's the graph of frictional force versus applied force. Your frictional force is the dependent variable. Applied force is your independent variable. Okay, so what is kept constant here? It's going to be what? The surface, or the coefficient of what? Of friction. Okay, then I'm applying a force of 10 newtons. My frictional force is also 10 newtons there. So which means that this object is still stationary. Okay, why am I saying still stationary? The applied force and the frictional force, they're at equilibrium, right? They're having the same magnitude but acting in opposite directions, right? I'm applying again a force of 20 newtons there. Okay, so I'm increasing this force. So can you see that my frictional force is also what? 20 newtons. Okay, which means that these two forces, they're still balanced, they're still at what? At equilibrium. This object is what? It's still at rest. Okay, then let's say here, right, you apply a force of what now? Of 50 newtons, and then an object immediately starts to do what? To move. Okay, then when the object starts to move, just before it starts to move, right, we have what we call the maximum static friction. So that is the maximum static friction. Okay, right, so that is the force that opposes the tendency of motion of a stationary object just before an object will start to do what? To move. So I'm having the maximum static friction there. All right, then immediately when now an object starts to do what? To move, what will happen? Right, then we are no longer talking about what? From this point to this point, we are no longer talking about what? The static friction, the maximum static friction. But what is that we talk about? Because an object now is in motion, we talk about the kinetic frictional frictional force. And what you need to know, the kinetic frictional force, Fk, it's going to be less than what? It's going to be less than what? Your Fs max. Okay, so you can see from this graph, and you can see after that it remains what? It remains constant. So you must understand what is going on here, right? So we are talking about the two types of forces, sort of frictional forces here, right? Your static friction and your kinetic friction, okay? Then this is a relationship between force applied and frictional force, okay? If you apply a force and then the object does not move, it means that the force that we are applying is equals to the frictional force. Then at a point where now the object will start to do what? To move, right? We have what we call the maximum static friction, which is the frictional force just before an object will start to do what? To move. Then after an object has moved now, right, or it's in motion, we talk of kinetic frictional force. And the kinetic frictional force, it's always less than the maximum static static friction, right? So I hope learners, this is making sense, ne? Right. Now let's talk about weight. Weight is another kind of a force, right? So and remember, weight or gravitational force, it falls under non-contact contact forces. So definition of weight, it is the gravitational force the earth exerts on any object on or near its surface. It is the gravitational force the earth exerts on object on or near its its surface, right? Then for example, in this case, you are having a table, we are having a book. So the table has its own Fg, gravitational force or weight. Even the book has its own what is this gravitational force. So it's a non-contact force. So what is gravitational force? It's the force the earth exerts on any object on or near its its surface. Then what is important again, this force always acts downward. Very, very important, ne? This force always acts in which direction? Downwards. You won't find Fg acting up or what is acting up, right? There's no way, right? So gravitational force always acts downwards. Gravitational force always acts what? Downwards. It is the gravitational force the earth exerts on any object on or near its surface. How do we calculate the gravitational force? We use this equation, right? Where this one is weight, that is W, it's weight, which is measured in newtons, is weight, or gravitational force. Okay, then M, this is the mass of an object, which is measured in what? In kilograms, right? G is there on our data sheet, right? G is a constant, which is 9.8 meters per second squared. Acting in which direction? Always acting in which direction? Downwards. Remember, learners, when it comes to the equation F net equals to MA, F net and A, they are what? They are directly proportional. Okay? So F net and A always acts in the same direction. Same even here. Weight and G, they're always acting in the same direction, and that direction is what? Is downwards. So you won't find a scenario where your weight or your Fg will act upwards. So it's always acting in which direction? Downwards. Okay, very, very important. Okay, so weight, that is what the gravitational force the earth exerts on any object on or near its its surface, right? So I'm sitting on the chair, all right? So while I'm sitting, right, so there's a force exerted by the chair on me, right, which is the normal force, all right? Then if the chair is a bit rough, then there is frictional force, but what type of frictional force is going to be what? The static friction, okay? Then if someone can push me, for example, right, but still I don't move, right, it means that the force that is being applied is equal to the static friction, all right? But when someone applies a force and I start to move, for example, all right, then it means that the force that is being applied overcome what? Overcome the static friction. Then now the frictional force becomes the kinetic what? Friction. But there is that special frictional force, which is what we call, or special static frictional force, which is what we call the maximum static friction, which is the frictional force just before an object will start to what? To move. Okay, so that is very, very important, learners. So we have talked about 4 kinds of forces. The normal force, actually it's going to be what? 3. So it's normal force, the frictional force, which is static and kinetic frictional force, and also what? Weight. Now let's look at these examples based on different kinds of forces. Okay, you have a crate here of 10 kilograms across a rough surface. Okay, so crate of 10 kilograms. The surface is what? It's rough. Immediately when they say the surface is rough, it means that here there is what? There's frictional force, right? The magnitude of the friction just before the crate starts to move is, so if they're saying just before the crate will start to move is, so actually here given what? Maximum static what? Friction, which is 80 what? 80 newtons. Okay, then just after the crate starts to move, the friction or frictional force changes to what? To 60 newtons. By now, I hope you understand that your maximum static frictional force will always be greater than your kinetic frictional what? Force. Okay, so hence here you see 60, but here you see what? You see 80. Okay, so the graph that we were looking at talks about this. Okay, all right, then just after the crate starts to move, the friction changes to 60 newtons. What are they looking for? Calculate the value of the coefficient of static what? Static friction. Okay, so there's only one equation where we have static what? Friction. The equation is Fs max equals to mu s what? N. Ne? Okay, so for us to get the coefficient of static friction, we need the normal force, we need Fs max. So already we have Fs max, which is 80. But now we can see we are having how many unknowns? 2. While we are looking for what? For mu s, which is the coefficient of static what? Friction. So first thing that you need to do here is to start by drawing what? A free body diagram, right? So I'm drawing my free body diagram here, although we are still going to talk more about that, right? So I'm drawing my free body diagram here. I'm having Fg, and then I'm having what? The normal force. Okay, so what is important here, because this object is stationary, all right, initially, since they're looking for a static coefficient of static friction, so they're talking about the stationary what? The stationary object. So if an object is stationary, it means that forces are at equilibrium, right? Forces are at what? Equilibrium. So if the forces are at equilibrium, it means that this Fg and this normal force, they are equal in what? In magnitude, but acting in opposite what? Directions. Okay, so how can we get the normal force in this case? We can start by calculating what? The magnitude of the gravitational force using the equation Fg equals to mg, or weight equals to what? Mg. So what is the mass of this object? We have used the equation. What is the mass of this object? The mass of this object is 10, and then what is g is 9.8, and then here I'm having what? 98. It means that if this one is 98 newtons, even this one is what? Is 98 what? Newtons, but in the opposite what? Directions. So my normal force is also what? 98 what? Newtons, right? Then go straight to that equation. maximum static friction is 80, okay? Then mu s times what? Times the normal force, which is 98 newtons. Then we go to what is 0.82. Okay. Then another one, Jabu drags a chair across the floor to a table. Okay. The mass of the chair is 1.3 kilograms. The coefficient of kinetic friction is 0.71. Calculate the size of the frictional what? Frictional force. So the equation that we have, it's Fk equals to mu k n, right? Because they are looking for what? The kinetic what? They're looking for what? Frictional force. But what type of frictional force? It should be kinetic frictional force, since we are given the coefficient of kinetic frictional force. Okay, right. Then, so what is it that we need here is mu k, which is this. Okay, right. What else is given? It's mass. And then do you have any other thing given here? No. Right. So they are looking for what? For Fk in this case. So your mu k is given, but first thing that we need to do there is to calculate what? The normal what? The magnitude of the normal what? Normal force. Okay. Then your normal force in this case is equals to what again? Mg. So start by calculating mg, and then your mg will be equals to what? The normal force. Okay. Right. Then your Fk equals to mu kn, and then your coefficient is given is 0.71, and then your normal force, which is equals to Fg in this case, is 12.74. Then the answer here for Fk is what? Is 9.05 what? Newtons. All right. So these are the equations, so the calculations, right? Calculating the weight, calculating the static or the maximum static frictional force, and also calculating what? The kinetic frictional force. Okay, right. Then force diagrams and free body diagrams. This is very, very important, especially for Newton's laws and application. If you are unable to draw a correct free body diagram or correct labeled free body diagram, you are going to have a problem when it comes to solving problems, when it comes to actually your paper one. So very, very important. You must master how to draw free and force diagrams. Yeah, right. So when it comes to a force diagram, when you talk of a force diagram, free body diagram, those are the diagrams of forces. All right. It's just that when it comes to a force diagram, right, the object there is represented by a square box, right, and the forces acting on that object, they are either pointing towards or away from that box. Okay, that is a force diagram. Still, it is the diagram of forces. Free body diagram is also a diagram of forces. But why is it different from the force diagram? It's just that when it comes to a free body diagram, the object is represented by a dot. So it's free of its body, right? So the dot represents what? An object. And when it comes to a free body diagram, we have to make sure that forces are always pointing away from the dot. Forces are always pointing away from the dot. That is a free body what? Diagram. A force diagram represents an object by a square box, but forces can either point towards or away. It doesn't matter. That is a force diagram. But when it comes to a free body diagram, represent an object by the dot, and forces, they must point away from what? From the dot. And these forces, they must start from the dot. So the tail of these forces, or the tails of these forces, they must start from the dot. Okay? Same even when it comes to a force diagram. The forces, they must start from the box, or they must be in contact with what? With the box. Very, very important. Even when it comes to free body diagrams, those forces, they must be in contact with what? With the dot. It's just that those forces, they must point away from what? From the dot. So that is the difference, learners, between force diagrams and free body what diagrams. Okay, right. So these are the examples of what free body diagrams and force what and force diagrams, right? So here you are having a track there, right? There's a force that is applied of 1,500 newtons. There's frictional force of 345 newtons. Obvious, there's gravitational force. There's also what? The normal force. Okay, so they want us to draw force diagrams and free body what diagrams. So this is the free body diagram, right? You start with a dot, okay? Then we have a force of 1,500 newtons. You have a force of friction, which is 345 watt newtons. So look at these arrows, right? This and this, you can see that these two, they are not what these two are not what are not equal, ne? So this is 1,500 newtons. This is 345 watt newtons. So you can see these two forces that are not equal in what? In magnitude. If they are not equal in magnitude, we have to show that even when it comes to our free body diagram, you can see my force applied is longer than my frictional force. All right? So my applied force is longer than or is greater than my what? My frictional force. So this arrow greater than or is longer than this one, which shows that the magnitude of force applied is greater than the magnitude of what? Of frictional force, right? Then your Fg is 5,000 newtons, and your Fg will be equal to your what? Your normal force, which is also 5,000 newtons. Okay, so that is our free body diagram. Force diagram. This is the force diagram. You have your what? Your force applied. Okay. You have your frictional force, which is a bit shorter than the force applied. Right? So frictional force. And then you have your Fg. Very, very important. You have your what? Your Fg. You have your what? Your normal what? Your normal force. So that is our force diagram. So the difference is just that when it comes to a force diagram, you represent an object by a box there, but free body diagram, you represent an object by what? By a dot. So that is an example of drawing free body diagrams and force what? Diagrams. So more examples here, all right? Sci-Bono pushes a crate of mass 20 kilograms on a rough horizontal surface. So you need to underline that. So they're saying the surface is what? Is rough. So there's what? There's friction there. Okay? With a force of 100 newtons to what? To the right. Okay? So frictional force acting on the crate is 20 newtons. Draw force and free body diagrams indicating all the forces acting on what? On the crate. Okay? So they've started, you can see, they've started with what? With a force diagram. So I'm having my what here? My Fg, you can see that. So represent an object by what there? By a box. I'm having my Fg. I'm having my normal force, which is always acting perpendicular to the surface. I'm having a force of 100 watt newtons and also a force of 20 newtons in the opposite what direction. That is frictional force. So even if this was this side, let's say we had something like this. You have your Fg, you have your normal force, you have your 100 newtons, which is the force applied, and you also have what? Your frictional force, which is what? 20 newtons, right? So you can even draw it like this, especially this one, all right? Because remember here, when it comes to force diagrams, forces can either point towards or away. This is the free body diagram. You can see all forces are starting from the dot, okay? I'm having a force applied, a frictional force, which is shorter than what? the force applied, right? You have Fg there, which is 196 newtons. You have the normal force, which is also supposed to be what here? 196 what newtons, but in the opposite what directions. Okay, so this is our free body diagrams and force what diagrams on the horizontal what surface. Learners, there's another thing that I want to address here. Yeah, is the issue of the normal force. How do we calculate the normal force? All right, the normal force here for this scenario, the normal force is equals to negative what weight, right? These two forces are acting in opposite what directions, but they're at what? At equilibrium. Okay, so if they're at equilibrium, I think we have to start here. You have your normal force plus into minus what? Oh, you have your normal force plus what? Your weight, which is equals to what? That is our F net, right? So I'm normal force plus weight equals to what? Our net here is what? Is 0, because the forces are at equilibrium. Then your normal force will be equals to what? Will be equals to what? Weight, name, or negative what? Or negative weight, which is equals to what here? Mg, right? So what I want to say here is that the normal force is equal to weight, right? When it comes to a scenario where a force is applied parallel, you can see this 100 newtons is applied parallel to what? To the surface. Okay, so your normal force will be equal to Fg. Okay, so draw a free body diagram. Already you have drawn a free body diagram, but in this case your normal force is equal to what? Gravitational force, which is equal to what? Mg. I'm talking about what here? The magnitudes. Very, very important, learners. So the issue of the normal force here is the key, because remember, frictional force depends on what? On the normal force. So hence it's very, very important for us to understand how to calculate the magnitude of the normal force. So on a scenario where an object is stationary on a horizontal plane, for example, your normal force will be equal to mg again, right? In this case, where a force is applied, you can see a force is applied parallel to the surface. Your normal force again is still equal to what? Mg. Okay? Then after getting normal force, you are aware that you can even move further, calculate the maximum static friction, calculate the kinetic frictional force. But what is important here is to understand how to calculate the magnitude of the normal force. Object stationary, right? Object pulled with a horizontal force, pulled with a horizontal force of 100 newtons, for example, your normal force is still what? Mg, okay, or equals to Fg there, right? Then let's look at this scenario. You have a force that is applied at an angle to the horizontal, right? Okay, let's draw our free body what diagram. So free body diagram, I'm going to have my what? My Fg, which is acting downwards. I'm going to have what? My normal force, okay? All right? And then force that is being what there? That is being applied, okay? Then there is frictional force, which is the force that is going to oppose the motion. So if the motion is to the right, then your frictional force will act in the opposite what? Directions. So this is our free body what? Diagram. Same with our force diagram. Then what? Frictional force. So I'm having a free body diagram and a force what? A force diagram. Then what I want to talk about here again, learners, is the issue of the normal force. Remember, normal force is equal to mg, when an object is stationary, right? Okay, on a horizontal plane. Okay, normal force is equals to mg again, where now an object is pulled along a horizontal surface with a horizontal force. For example, the horizontal force, it was what, 100 newtons. Okay, therefore the normal force there is still going to be what, mg. Now the problem starts here, where now a force is applied at an angle to the horizontal. So already you know how to resolve a force into its what, components. So for you to get the magnitude of the normal force, resolve this force into its what, components. So when I resolve this force into its components, I'm getting what, Fy and what, and F what, and Fx. Okay, so how many forces now are acting vertical? It's 1, 2, 3, right? The forces that are acting vertical after resolving that force into its components. How many forces are acting vertical? Normal force, Fg, and what? And Fy. So by now you know how to resolve a force into its what, component. So if it's 1, 2, 3, now I'm looking for the normal force. Normal force plus, right, Fy plus into minus what, Fg, since they're acting in opposite directions, will be equals to what, 0. Why is it 0? Vertical forces are at equilibrium, right? Since an object is moving on the horizontal what, plane. This object is not moving up and down, but is moving on the horizontal what, plane, right? Which means that the vertical forces are balanced, they're at what, equilibrium. Very, very important. Unless if an object was moving up and down, just like that. Ne? But since the object is moving on the horizontal surface, right, the vertical forces are at equilibrium, or the vertical forces are balanced. Okay, then so there are 3. So it will be normal force, right, equals to Fg minus what, Fy. That will be our what, our normal force. If a force is applied at an angle like this, or pulled at an angle to what, to the horizontal, ne? Then so these are the solutions, all right? Then scenario number 3, you can see that this one is pushed at an angle of what, of 10 degrees. Start with your free body diagram. You have your what, your Fg. You have your what, your normal force. And then you cannot kill the dot. Very, very important. When you draw a free body diagram, forces, they must point away from what? From the dot. So hence here we'll have what? This force F. Okay? Then you have your what? Your frictional what? Your frictional force. So how do we calculate the normal force in this case? You have a force that is applied at what? At an angle. So resolve that force into its what? Components. I'm having Fy, and then I'm having what here? Fx. Okay? Then the object moves on the horizontal surface. It's not moving up and down, right? So if it's like that, it means that the vertical forces there, they're at what? At equilibrium. How many vertical forces? 1, 2, 3. So it's going to be normal force, right? Minus Fg minus what? Fy equals to 0. Okay? Therefore, the normal force will be equals to what? Fg plus what? Plus Fy. That is very, very important. Okay? So we are dealing with what? Object on the horizontal surface. Single object on the horizontal surface. We started with what? With the stationary object on a rough horizontal surface, right? Stationary object on a rough horizontal what? Surface. Normal force being equals to mg in that case. Okay, then we move to the second scenario, where now an object on the horizontal plane is pulled with a horizontal force, right? So there was a horizontal force of 100 newtons pulled with a horizontal force. Then your normal force in that case again will be equal to mg. Why is it equal to mg? Because there are only two vertical forces, right? And this object is not moving vertically upwards or vertical downwards. It means that the vertical forces are at equilibrium, right? So if there are only two vertical forces, right? Okay, and those two forces are at equilibrium, if one force is 50 newtons, the other one is also going to be 50 newtons, but in the opposite what directions. Hence, we said your normal force will be equal to mg in that case. Okay, here, or this one, a force here is applied at what? At an angle. So this object is pulled is pulled on the horizontal surface by a force of 30 newtons to the horizontal. Okay, so you draw your free body diagram, you draw what you see actually. Then from there, if you want to calculate the magnitude of the normal force, you don't have a choice. You have a force that is applied at an angle to the horizontal. So you don't have a choice. You have to resolve that force into its components. Then after resolving, check the number of vertical forces that are acting on that object. Here it was 1, 2, 3. If it was 1, 2, right, then they were going to be of the same magnitude. Ne? But now there are 3. Okay, so you add the 3 of them, equate that to 0 because they are still balanced since an object is moving horizontally, not vertical. Then try to find the magnitude of the normal force there. It will be Fg minus Fy. Here, pushed at an angle to the horizontal, same thing. Draw your free body diagram nicely so. Then from there, what are you supposed to do? Because a force is applied at an angle, resolve that force into its components. Why are you doing that? It's because you want to see all the horizontal forces, you want to see all the vertical forces. So there's an additional force, vertical force now, which is going to be your Fy. So I'm having normal force Fg and Fy. So I need to add those 3 and equate to 0 because this object is not moving vertically upwards, for example, is moving on the horizontal plane, which means that vertical forces are at what? At equilibrium. Very, very important, learners. So hence I have 1, 2, 3. Then add the 3 and then find the magnitude of the normal force. Then the magnitude of the normal force will be Fg plus what? Plus Fy. These are some of the things that are very, very important, especially for your calculations. Remember, for you to get the magnitude of the frictional force, you need the magnitude of the normal force. So which means that if you don't know how to calculate the normal force in different scenarios, you are going to have a problem when it comes to calculating what? The frictional force. Because normal force is needed when it comes to the calculation of what? Of frictional force. Clear, ne? Right. So vertical plane, we have focused on horizontal plane. Now let's focus on the vertical plane. Here we are having a light bulb hanged from the ceiling. So if it's hanged, right, it's not moving, right? So what are we having here as our free body diagram, right? You have your Fg. Remember, it's an non-contact force, this one. Then you have tension because there's rope there. Then there's what? There's tension. Okay? So there's tension, there's Fg. Right? So there's tension and there's what? There's Fg. Alright, so these are the two the two forces. So maybe I forgot something here to talk about the tension. If you talk of tension, that is actually the force on the rope, the force on a cable, the force on a tow bar, for example. So for example here, in this case, we are having the ceiling, right? There is a rope, right? And then there is what? A light bulb there, okay? So when you talk of the tension, right? So that is the force on the rope, the force on the tow bar, for example, or the force on what? On the cable. Okay? Rope, string, cable, tow bar. So you will have tension there. Okay? All right? So you have tension because of that cable. Okay? So it's either cable, rope, tow bar, right? Or string. So that is the force on the string, the force on the rope, the force on the cable, the force on what? On the tow bar, which connects the two objects. Okay, then that is going to be what? Tension, right? Then so here there's Fg, there's what? There's tension, and Fg and tension, they're equal in what? In magnitude, because this thing is hanged, is not moving. So these two forces are at what? Are at equilibrium. So you can draw your force diagram again, where you will have your Fg and your what? And your tension. So the symbol for tension is capital letter what? T. So in tension, that is the force on the rope, that is the force on the string, and that is the force on what? On the cable, or the force on what? On the tow what? On the tow bar. Ne? Alright. Then that is vertical what? Plane. And we can see when it comes to vertical plane, there's no normal force because there's no surface there. Remember, it's the force exerted by the surface and on an object that is in contact with. Okay? So there's no normal force on what? On the vertical what? Plane. Right. Then it's still vertical plane, this one. Now let's move to what? To an inclined plane. So a crate at rest on a slope. So this crate is at rest, is stationary, okay? And to be honest here, right, even if they didn't mention that, obviously in this case, they didn't mention that whether the surface is smooth or rough. But what we can say here is that this incline is rough, because if it was smooth, this object was not going to do what? To be stationary on this incline. It was just going to move downward, down the slope, because of Fg what? Fg parallel. Okay? So, but our focus for now is to draw a free body what? Diagram. So free body diagram, first thing that I have here is my Fg. Fg is always acting downwards, right? Then what am I having here? I'm having the normal what? The normal force. Normal force always acts perpendicular to what? To the surface. So this is the surface, then you'll have what? 90 degrees, right? Then there is also what? Frictional force, which is the force that is going to oppose what? The motion or the tendency of motion of a stationary object relative to what? To the surface. So here I'm having Fs because the object is what? Is stationary. Okay? Then another thing which is important here, this is how we have to draw our free body diagram, right? So this is the incline, right? So your normal force should act perpendicular. Then this other one, which is your Fg, should act in which direction? Downwards. Frictional force is the force that opposes the motion of an object, right? And it acts parallel to the surface. So it should act parallel to what? To the surface. So it should act parallel to what? To the surface. So that is going to be what? Your frictional force. And what type of frictional force would be the static what? Friction. Why am I saying static friction? The object is at rest. Okay? So if we assume that this surface is smooth, then this object was not going to be stationary on that inclined plane. So the reason why it is stationary is because of what? The static frictional force, which opposes the motion of what? Of an object. Okay. Then when it comes to an incline, we can resolve weight into its what? Components. Okay. So when you resolve weight into its components, so the components of weight is Fg parallel and what? And Fg what? Perpendicular. That is the parallel component of weight and the perpendicular component of what? Of weight. So parallel component of weight is always acting down the slope. We can see here, right? And then perpendicular component of weight is always perpendicular to what? To the surface. Okay. So this is the parallel component of weight, which is always acting down the slope. It doesn't matter whether an object is moving up the slope or down the slope, but your parallel component of weight is always acting down the slope. Again, same with the perpendicular component of weight, is always acting perpendicular to the incline, whether the object is moving up the slope or downward or down the slope. So on an inclined plane, we can resolve weight into its what? Components, which is the parallel component of weight and the perpendicular component of what? Of weight. But only when it comes to an inclined plane, not on the horizontal plane or vertical plane. We only resolve weight into its components on an inclined plane. How do we resolve? Your FG parallel is always acting down the slope, whether an object is moving up the slope, stationary, is moving down the slope, it doesn't matter, right? Then your FG perpendicular is always perpendicular to what? To the surface. Same with the normal force, which is always acting perpendicular to what? To the surface. That is very, very important. Then how do we calculate FG parallel and FG perpendicular? Your FG parallel is given by what? Weight sine what? Sine theta, which is the same as mg what? Sine theta. FG perpendicular is given by weight cos theta, which is the same as mg cos what? Cos theta. What is this theta? Is the angle, that 15 degrees is the angle of what? Of inclination. Okay, so that is an inclined plane, free body diagram on an inclined what? Plane. So when you draw a free body diagram, learners, we don't want to see the components of weight, for example, when it comes to what? An inclined plane. We don't want to see the components of a force, for example, if a force is applied at an angle. No. You will only resolve a force into its components, or you will only resolve weight into its components, right? If you want to do calculations. For example, in this case, the reason why we are resolving this weight into its what? Components is because we want to get the magnitude of the normal force, right? So in this case, your normal force, so you just need to check forces that are perpendicular there. How many are they? There are only two. And then this object is not moving up, down, right? But is moving up the slope, down the slope, which means that these two forces, they're at what? At equilibrium. If they're at equilibrium, therefore your normal force will be equal to Ft what? Perpendicular. Very, very important. In this case, your normal force is equal to Ft what? Perpendicular, which is given by what? Mg what? Cos what? Cos theta. That is how we have to calculate what? The normal force. Very, very important. We have talked about the three planes there. It's a horizontal plane, object stationary on a rough horizontal plane. Your normal force equals to Fg. Object moving on a rough horizontal surface, a force is applied parallel to the surface. Your normal force is equals to what? Mg. But now when a force is applied at an angle, pulled at an angle to the horizontal, then your normal force there, very, very important, is equals to what? Fg minus Fy. I've shown you how to get to that Fg minus Fy. Then you move to a force pushed at an angle. You start by resolving, right, for you to get the normal force. Then your normal force will be equals to what? Fg plus what? Plus Fy. Then come to an inclined plane. For you to get the normal force, resolve weight into its components so that you will see all the parallel forces to the slope and all the perpendicular forces to what? To the slope. Then you can see there are only two. If there are only two and you are all aware that they are balanced, then if they are balanced, therefore they are what? F net will be equals to 0. Hence, the normal force here will be equals to Fg what? Perpendicular. So I hope, learners, this is making sense, ne? And I think for today what we have done is enough, right? But just to recap on what I did here, so that you'll understand these calculations, ne? We did some calculations here, okay? So Jabu drags a chair across the floor to a table. So this is the floor, for example, and then the chair Let's say this is a chair. I can even use a box here. So it's dragged across what? The floor. Okay? So it's dragged horizontally. Okay? Then there's a force that opposes what? The motion, which is Fk in this case, because the object is in what? In motion. Okay? Then we are given the mass of the chair as 1.3. Okay? What are they looking for? Calculate the size of the frictional force, given that the coefficient of kinetic friction is 0.71. Where do you start? Fk is given by mu kn. Where is this equation coming from? It is there on the data sheet, so there's no need to memorize it. Ne? So I'm looking for Fk, but I don't have normal force. But what I know that when I draw a free body diagram for this scenario, I'm having the normal force, I'm having what? Fg, I'm having force applied, and I'm having what, for example, the kinetic frictional force. I know that if a force is applied parallel to the surface, my normal force will be equal to Fg. Hence, we did this. So this is normal force equals to what? Fg. Then after getting the normal force, then go straight to that equation where there is n, substitute by the value that you got, then get Fk in what? In newtons. So we'll talk more about this, but our focus today was different kinds of forces. Ne? So they're divided into two categories. You have contact, you have non-contact. So they act over a distance. Those are the non-contact. For example, your electrostatic force, your magnetic force, and also your what? Your gravitational force. Then contact forces, those are the forces exerted by objects that are in contact. For example, your applied force, your tension, your frictional force, your normal force. Then we move to normal force. We define normal force as the force exerted by the surface on an object that is in contact with, and the normal force is always acting perpendicular to the surface, right? Then you move to what? Those scenarios. How do we calculate that normal force? If an object is stationary on a horizontal surface, normal force equals to Fg. Okay? If the force that is applied on an object is applied parallel to the horizontal surface, again, your normal force will be equal to what? Fg. But now in a case where the force on the horizontal plane is applied at an angle to the horizontal, right? It's either your normal force will be equal to Fg minus Fy, or Fg plus what? Plus Fy. If it's pulled, it's Fg at an angle is Fg minus Fy. Pushed at an angle is Fg minus what? Fy. Okay, and I've shown you how you got to that Fg plus Fy, Fg minus Fy, right? Then on a vertical plane, no normal force, right? And then inclined plane, the normal force will be equal to Fg what? Perpendicular. Then we move to frictional force. We define frictional force as a force that opposes the motion of an object and it acts parallel to the surface. And then again, your frictional force depends on the normal force. Okay, you can see even when it comes to this equation, we need what? The normal force for us to get what? The frictional force. Okay, then there are two types of frictional forces, which is your static frictional force, which is the force that opposes the tendency of motion of a stationary object relative to the surface. And we have what we call the maximum static frictional force, which is the frictional force just before an object will start to move. And how do we calculate that? It is given by Fs max equals to mu s, which is the coefficient of static friction, times the normal force. Okay, so we can calculate that. Then your kinetic frictional force, that is the force that opposes the motion of a moving object relative to what? To the surface. So when an object is in motion, we talk of kinetic frictional force. And how do we calculate that? It is Fk equals to mu k what? Mu kn, where Fk is the kinetic frictional force, mu k is the coefficient of kinetic friction, then n is the normal what? Is the normal force. Okay, then again the issue of the graph, the relationship between frictional force and applied force, right? when you apply a force, the object, let's say the object does not move, right? It means that the forces there at that moment, they are balanced. If it's 10 here, then there is also going to be what? 10. You move toward foot again, is 20. Even here is going to be what? 20. Still the object is not what? Moving. Then when it is about to move, it's where you have your what? Your Fs what? Your Fs what? Fs max. And what happens? Your Fs max is always greater than your what? Your Fk. So it's what we talked about today, and we are still going to focus more on the free body diagrams moving forward. But for today, I think it's enough, and we don't want to confuse you, right? So thank you so much, learners. See you next time. Bye bye.